We all have our failures. If you work in a shop, you probably fail more than others. Sometimes you recover, sometimes you start over. Rarely you give up, but always you learn something. And sometimes you even learn how to use failure to your advantage. Welcome back to Inheritance Machining. If you haven't already figured it out from the incredibly ambiguous intro, this video is about burnishing. Spelled like furnishing but with a B, and terrible jokes aside, burnishing is a machining process for making very smooth surfaces, through failure. In theory, it works by pushing or rolling something hard into something soft. A lot like cutting, but there's no material removal. Just a whole bunch of squishing. Of course, squishing means there's a force component to all this. Too little force and the material just bounces back. This is called elastic deformation and will not result in burnishing. Push harder though and the material moves out of the way and stays there, exceeding the failure point of the metal in what's called plastic deformation. Do this over and over and you can take a microscopically rough machined surface and turn it into something with a mirror finish. This is burnishing. It's also a machining process I've never done or even witnessed in person, so I think that makes me uniquely qualified to make my own burnishing tool. But before I rationalize why or if I need this, I'm going to ignore my prefrontal cortex and trudge ahead anyways, because I want that. Now I talked about burnishing making surfaces smooth, and smooth doesn't mean flat, so we can actually burnish round parts in the lathe. And considering I really like my lathe, it will be my travel companion for this initial foray. The burnishing tool itself is pretty straightforward. There's a hardened bearing ball to push into the metal that I want to burnish, a bearing for that bearing ball to roll against, this one is nice, and a beefy spring to adjust the force, because I don't really know how much is needed. Oh, and of course a design to hold it all together. A design that I'll make in Onshape, who I'm happy to partner with again because the more I use it, the more I love it. Imagine a professional grade modeling software that doesn't induce regular headaches, and I don't just mean from a modeling standpoint. With no software to install, update, or crash my computer, I don't have to worry about all the IT overhead usually involved with bringing a design to life, and because it runs off the cloud, it's easy to collaborate with others, which for me is just me, but I can also use it anywhere on any device, whether from the productive setting of the office or the leisure of the shop. And because there's no installation, all the updates are automatic, so now that Onshape has released their own integrated cam studio, I didn't have to do a thing to get it. Of course, I don't know what I'll use it for, but still, pretty sweet that they're constantly rolling out new features, including a new government plan for engineers and manufacturers that require US regulatory compliance like ITAR and EAR. Letter salad aside, I really like Onshape and I think you will too, but make up your own mind. Try Onshape for free at onshape.pro/inheritance machining. After quite a bit of flip-flopping, I've landed on this. It's got the ball and bearing up here in the nose where all the action will happen, a stem to guide the movement and transfer the spring load, an adjustment knob and thrust bearing to set that spring load, and of course a body to hold it all together that can be mounted in the lathe's tool post. Now some of these pieces are pretty complicated, so I'm going to get my machining legs under me and start with a knob, which I'll make from bronze for its good bearing qualities, but also it's really pretty and fun to machine, aside from the absolute fire hose of chips it makes. I've been getting in the practice of doing my turning in 2 steps, especially where there's a lot of material removal like this. First, a roughing stage where I leave a little on the diameters, both outside and in. This lets the material warp where it's going to warp before screwing up my dimensions. Then I make the much lighter finishing cuts that themselves won't have an effect at all. Being a knob clearly implies the use of one's hand. And where there are hands, there should be knurling. Except for one issue. This goofball didn't leave enough room to actually use the knurling tool. And of course it's not as simple as sliding the part out in the chuck because that's no bueno. This one little oversight means I have to completely swap chucks to the four jaws so I can regain that alignment. Of course this isn't important for knurling. This tool can accommodate a decent amount of eccentricity and still come out just fine. The threads, on the other hand, they need to be kept in line. Now because this spring came from the home of misfit coils and helices, I have no idea what its background is. By that I mean its spring rate. This formula I found suggested somewhere in the neighborhood of 152 pounds per inch, which is a lot, but I have faith that the pitch to diameter ratio of this thread will make it easy to adjust by hand. Just in case though, I'm going to add some scallops to the knurling for extra grippiness. No failures yet, and I'm getting pretty excited bringing this thing to life. Up next is the body housing thingy, the big rectangular part. A perfect use for this hunk of low C question mark. Now I said before that burnishing is great for making things smooth, and it should be said that smooth does not mean flat. For instance, these faces I'm cutting are flat, but if you look at them under a microscope, you'll see something that looks like this, which is flat overall in a mechanical sense, but definitely not smooth. This is basically what all machine surfaces will look like, and since we're getting technical, it's also why they aren't reflective. I mean, light does reflect, but the inconsistent facets cause it to shoot in all directions, which is why you generally don't see a clear mirror reflection. But when we burnish a machine surface, the repeated rolling of the ball will smooth out all those highs and lows into something that looks more like this. This does a much better job keeping all the reflected light pointed in the same direction, making the mirrored surface, which sometimes you want. There are more advantages, but we'll hit on those later because now we have a square bar we can start hacking in the shape. First with some rabbets, or slightly less confusingly, rebates. Basically I'm narrowing down each side so it will fit in the tool holder. And naturally some chamfers to make it look important. The true important feature of this part, though, is the bore, which is actually made up of multiple features that will be a lot easier to make on the lathe. I want this bore to be centered on the hole I just drilled, but also straight with the rest of the body. So while I'm setting this up, I'm indicating both for concentricity in the pilot hole and for straightness along the finished faces. It's a frustrating process of 2 steps forward, 1.9 steps back, but given half an hour, I got to something I was happy with. The secondary reason for this pilot hole was to make the job for this bigger drill a little easier. The depth, however, doesn't make it an easy task for the boring bar. I mean, I have enough length, but with how far I have to stick it out, I can guarantee that I'll have some chatter. I played around with the speeds and feeds a bit to find a happy place, which didn't exist, but then I remembered someone saying to pop a magnet on here, and yep, that actually kind of works. I'll use a threading bar to hollow out a thread clearance groove in here. Then swap to a right-hand threading bar so I can cut the threads themselves in reverse by feeding out of the part, which you could see if not for my expert camera work. That's it for the lathe work. Can you believe I made it through without making a single boring joke? Neither can I. Over on the mill is a pilot hole through the top and bottom, some sketch milling to form a short slot at both levels, then an access hole that will make sense later. Now that we have all the easy stuff out of the way, let's take on a really tricky part. The stem ball holder majig. I should really spend more time naming my parts. This is going to be the bit that does all the work, and speaking of work, let's talk about work hardening. One of the other theoretical advantages of burnishing is that it makes a surface tougher. It's a threefold mechanism. First, recall those pre-burnishing peaks and valleys. When these contact some other material, whether intentionally or unintentionally, the load gets concentrated on these peaks and the metal deforms. Which is why it's next to impossible to keep a freshly machined part free from scratches. But since burnishing removes those peaks, any contact stress gets more evenly distributed, making it more resilient to wear. Secondly, burnishing literally work hardens the surface, so it's inherently stronger. And thirdly, the work hardening causes something called dislocations in the metal's crystal structure, which is a whole thing, but it basically expands the entire surface, putting it in a state of compression. Kind of like tempered glass, and we all know how tough that stuff is. Anyway, enough science. We have a problem on the lathe. As expected, with all the material I just removed, the part warped, just like I mentioned earlier. So we have to finish turning this another way that doesn't try to force the material straight while I cut it, because it's just going to bounce back once I let go. But this won't happen if I turn between centers. And luckily the finishing cuts I need to take are light enough that I don't need to bother with a drive dog. There's plenty of driving friction from the chuck center itself. I did get a little ambitious with the fillet cutting tool at first, but you don't know where the limits are unless you find them, right? A little Scotch-Briting later and we have this, a baby seal clubber. But that's not what I'm after, so let's get to the fancy stuff on this end. First is the bore for the ball that makes this a ball burnisher. It's a two-step deal with a smaller diameter at the face so the ball doesn't just fall out. The rest of this is going to be at the mill doing what mills do best, making things square. I'm working my way towards this, but don't be fooled by how simple things look from this angle. When I turn this around, yeah, there's kind of a lot going on here. This is what happens when there are a lot of great, elegant, and simple burnishing tool designs online, but my ego is propped up largely by my sense of originality. And when I can't think of something more elegant or simple, I make it interesting. What's important is, I have a plan. The chamfer mill gave me a bevel like I wanted here, but left a lot to be desired on the rest of this. Nothing a fresh insert on the fly cutter can't rectify. It also takes care of the step-down section, and angling the sharp insert a little in the fly cutter let me undercut the corner for a bit of breathing room here, which I'm hoping will help me with assembly later. Of course I need a way to get the ball in from the backside of this bore, so plunging a ball mill in takes care of that. Bringing me to the tricky stuff. Corner rounds, semicircular pockets, cylindrical pins, words that usually have me running from my rotary table, but we're going to do all these right here in this vise. No, I didn't retrofit my mill with CNC, I just have the next best thing, the Volstro rotary milling head. I used this more than I wanted to in my last project, so I think I have a pretty good grasp on it. For the uninitiated, it basically lets me offset the spindle and sweep it through an arc. In other words, exactly what I have to do here. After roughing it out, I started making small adjustments to the offset to bring both the outer curve and the central pin to final size, but I'm not going to let it do all the work. This pin is for a bearing, and I want the fit to be as perfect as possible, and while a pin is literally the opposite of a bore, it's also kind of the same. So the boring head fits right in here. Now, if I did all that right, a thing of beauty. Still not finished though. After drilling and tapping a hole in the middle, we're going to set this aside for the time being and make the mating part, a cap that goes over this opening. It'll have a few functions, the first of which will be making a sort of reservoir around the bearing for some lubricating oil. The second will be to support the other side of the pin the bearing mounts on. When this thing starts taking load, I don't want it to bend or break. So I'm cutting some recesses in this cap to catch the free end of the pin and transfer that load into the rest of the assembly. The last purpose is probably obvious, keeping the bearing in place. So after milling this free from the stock and using half this project's total hours fettling this into place, I can do the finishing operations with these as a matched pair. Starting with the rounded corners, which I initially doofed on the radius setting but had a nice recovery, then separating from the collet block to drill and ream a hole in the shank for the spring limiting pin, pop a nice meaty chamfer on the remaining edge, and lastly drill and tap a set screw hole to keep the aforementioned limiting pin in place. Which means all that's left to do is assemble. Okay, I hate it. I mean, it works, but it's ugly. It just looks boring, and I can't have that. I have a couple ideas, though. Now that is cool. Why hide all the sweet inner workings where you can't even see them? Sure, it makes the whole thing slightly more dangerous, but that's why we all like this hobby, isn't it? Anywho, there it is, a ball knurling tool for the lathe. Let's give it a whirl. Now, I don't really know what parameters will make this work best, so I'm going to approach this empirically-ish. Of course, I'll need to prep some stock, so I'll start with some low-carbon steel. The feed rate here is 3 thou per revolution, which is on the finer end and doesn't have the most consistent finish on this lathe for some reason, but we'll see how it pans out. Again, I don't know what pressure is needed, hence the spring, so I'll start at 6 turns, putting me around 50 pounds of force when I also account for the 25 thou of engagement, and send the burnishing tool on its way at 3 thou per revolution. That was clearly not enough. Let's try gradually increasing the pressure. Each pass did seem to get slightly better, but still none of them are beyond a meh finish. Nor do they appear to have work hardened much. This 40 Rockwell C hardness file still has no trouble marking its territory. Let's try something different. A 6 thou per rev cut and burnishing at 167 pounds and 3 thou per revolution. But this time I'll do 1, 2, and 3 passes. Okay, there's definitely an improvement the more burnishing I do. Let's keep mixing it up. A 9 thou per rev cut leaves a noticeably coarser starting finish. But even after burnishing at the same settings with coolant for 3 passes, the original coarseness still comes through. One more test with a 6 thou per rev cut and 1, 2, and 3 passes with the burnisher. I think that's our guy. The finish is noticeably more reflective. Actually, I wonder if... Okay, it just keeps getting better and better the more passes I take. I think that might be the trick to all this. Just burnish it to death. The hardness did get a little better. The file doesn't completely dig in like before, but still not the change I was expecting. On the other hand, the dimensional accuracy pre- and post-burnishing is astounding. Well below 1/1000th of an inch, and that honestly could just be the taper in this shaft. Let's try some other metals. Okay, this works, but also doesn't. I keep getting a sort of orange peel-like finish on both aluminum and bronze. These are much softer metals, so I tried cutting the pressure in half, but it still had the same effect. Let me know what you think is going on here in the comments, because I'm at a loss. In the meantime, there is one more thing I want to try.
What do you have? Ooh!
Right? It's almost like a perfect mirror finish.
It did not occur to me you could use it in that direction.
Yes, you can use it in all, well, not this tool, but you can burnish in all directions.
It's a very fancy.
It's so fancy.
It looks very soft.
It's not, you don't touch it.
That's very soft.
Soft. You can see the little distortions in it, but it's largely from the starting surface not being super smooth. I did a thing.
You did do a thing.
Yep.
Okay, so I'm reasonably impressed, but not completely blown away by the outcome. I'm sure there are things I could do better, and if you have an idea on those, let me know what you think. Burnishing flat surfaces like this, though, definitely has my gears turning on where else I could use this technique in the shop. But that's not for this video. As always, thanks for watching, and see you next time.